Okay, so I've received a few questions about writing the standard matrix for a transformation. So I wanted to create a video to go over that. So first, just the theory behind the method here. The idea is we want to write a matrix, we usually use A, so that the transformation of X, so like T of X, is equal to this matrix A times X. And in that case, we call A the standard matrix of that transformation. Now, there's this theorem in section 1.9 that talks about an efficient way of doing this, which is you input unit vectors as your vector X. So T of E1, which, by the way, the notation here, so E1 is a vector of an unspecified size, but where it's got 1 in the first position and zeros everywhere else. So if it's in, say, R3, then it's going to be 1, 0, 0. Or if it's in R4, it's going to be 1, 0, 0, 0. Or if it's in R2, it's 1, 0. Okay, you get the idea. Point is, it's got a 1 in the first position, zeros everywhere else. So if you do this matrix A times E1, you've got a 1 in the first position. So if you think about the way the matrix vector product is defined, you have the first entry of this vector, which is 1, times the first column of A. I'm going to call that C1, column 1, plus the second entry in this vector E1, which is going to be 0, times the second column. And all of the other entries in E1 are going to be 0. So you're going to have 0 times every other column, dot, 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 dot. So you're going to end up with, every time, you're going to end up with 1 times column 1. So you end up with just column 1. If you do the same thing, but with E2, so that's equal to A times E2. Now we're talking about this matrix A times this vector that's got a 1 now in the second position and then zeros everywhere else. So you're going to end up with 0 times column 1 plus 1 times column 2 plus 0 times everything else. So you end up with just column 2. And so kind of zooming out on this then. So the big picture is, if you do the transformation to the first unit vector, that's going to generate the first column of A. And if you apply the transformation to the unit vector, with 1 in the next component, then that's going to generate the second column of A. And then you could keep doing this as long as you need to, depending on the size of the dimension of the space you're working in. Okay, so having said that, that's our plan. And it's, like I said, summarized in a theorem in section 1.9. Here's a couple of problems where we can apply it. So write the standard matrix of a transformation from R2 to R2. By the way, this right here is telling you that the input is a vector in R2, the output is a vector in R2, which reflects each vector over the y-axis and triples its length. So as far as test questions, I prefer this kind of question, where you can draw yourself a picture to figure it out. So if we want to find, let's say, column 1 of the matrix A, what we can do is apply this transformation to the first unit vector. So if we're talking about R2, that's just going to be 1, 0. And here's where you can draw yourself a picture. And I might actually get rid of a lot of this right here. Let me delete to clear some space. So I can draw. I'm trying to draw. Okay. Over here. Okay. So 1, 0. We can represent that as a vector going from the origin to the point 1, 0, which I'm going to kind of... Ooh, I don't want to space this out too far. Well, okay. Sorry guys, let's see. So let's say this is 1, 2, 3, because I noticed that we're going to end up tripling the length of these guys, so I'm going to put 3 units out in each direction. 1, 2, 3, I think that's... Okay. So 1, 0 is this vector from the origin to the point 1, 0, so that's this guy right here. This is E1. Now if we apply that transformation, so we want to reflect it over the y-axis. I'll draw the new vector in green. Was this blue here? Reflect it over the y-axis, so it's going to point in this direction now, and triple the length. So if it's 1 unit long right now, then if we triple the length, it's going to be 3 units long. Reflected in the opposite direction, reflected over the y-axis. So this is going to be t of e1, which is the vector, well, it's pointing to the point -3, 0. So this is the vector -3, 0. So that's going to be column 1 of this standard matrix A. We can start to build our matrix down here. Column 1 we know now is going to be -3, 0. Now to find column 2, we apply the transformation to E2, the second unit vector, which, so for R2 that's going to be 0, 1. Okay, so let's draw the picture over here. So E2, the vector 0, 1. So it's going to be, I like to draw it as a vector from the origin to the point 0, 1 right here. So here's E2. If we apply this transformation, so reflect it over the y-axis, well, if it's sitting on the y-axis, it doesn't reflect anywhere, and then triple the length. So if we triple the length, it goes from 1 unit long to 3 units long. So this is t of E2. And so t of E2 is the vector 0, 3. And so that's going to be the second column of this matrix A, 0, 3. And now you've got the standard matrix for this transformation. So that's one way to do it. If the transformation is described geometrically like this, and it's something that you can draw and figure out the coordinates, then that's probably the easiest way to handle those problems. Now, with a couple of problems in my math lab, you can't really eyeball these. You can't really just draw a picture and figure out the exact coordinates just based on your drawing, the way I did with this first example. And this is the one that I've gotten a lot of questions about in the GroupMe. And I don't have that formula handy. Hang on, I'm going to pause. It's not one that I use a lot. Or no, I don't have to pause. I'll dig it out in a second. Okay, but the overall approach is the same. You could use a unit circle to figure these out. So if we want to write the standard matrix, well, yeah, so I don't really want to go through all the steps, but you can go through this same logic and come up with a certain formula, which is in the textbook in section 1.9. And I'm going to pause this just for a second while I open to the page. Okay, so I opened the textbook to the formula, but I also thought about, this is something we could talk about, maybe real quick where this comes from. So suppose we take the same approach. Column 1 of the matrix A will equal T of E1, and we're still talking R2 to R2, so E1 is this vector 1, 0. Now, instead of specifically this -5 pi over 3, I just want to think in terms of, you rotate it, let's say theta radians. So if you start with your vector E1 right here, let's say this is 1 unit long, and then you rotate it theta radians, let's say this is theta radians right here. So now this time all we're doing is rotating. It's still 1 unit. 1 unit long, even though the way I drew it looks kind of longer. But this is T of E1. Well, the coordinates here, if this is still 1 unit in length, this is a point on the unit circle, which if you remember this stuff about reading values off the unit circle, the x coordinate right here would be given by, or the x coordinate gives you the value of cosine of theta when you're reading the unit circle, and the y coordinate of this point gives you the value of sine of theta. So we're just kind of using that backwards. Again, this is when it's rotated theta radians. Rotated theta radians. Now, column 2 is a little bit trickier. Oh, but by the way, if I'm building the matrix A over here, so the formula, it's given in an example in 1.9. I'm using the previous edition of the textbook. This is the 5th edition. It's on page 73. So if you're using the 6th edition, which is the current edition, it'll be probably somewhere around there. Okay, I couldn't find where my mouse was. So column 2 of A is equal to T of E2, which is 0, 1. Okay, so like I said, this is a little trickier. We have column 1. It's cosine of theta, sine of theta. And I started to say if you look at the formula in example 3 and 1.9, that's what it gives you for the first column. Now for the second column, I'm going to draw a new picture here. So E2 is this vector. Let's say that's 1 unit in length. If you rotate that theta radians, so let me scooch this down a little more. Then, so I'm going to draw it so it looks like about the same angle measure here, theta. And I keep making the transformed one too long. Okay. Then let's say this is T of E2. So I was saying this is a little bit trickier because in trigonometry, if you remember, the angles, when we set them up in standard position, it always starts from the positive x-axis. So that lines up perfectly with our E1 vector. So it lies on the positive x-axis. For E2, it lies on the positive y-axis. So we've got this theta radians here, and then we've got this additional 90 degrees right here, or pi over 2 radians. So T of E2 here is actually going to be, the x-coordinate will be not cosine of theta, but cosine of the theta radians here plus 90 degrees. And the y-coordinate here will be sine of this angle, which is sine of the angle theta with an additional 90 degrees. And now if you use some formulas from trigonometry, so here's where I'm going to wave my hands a bit. I'm not going to go through the details of the trig, but if you look at the angle addition formula, that's what you should look up if you want to fill in the blanks here. It's angle addition formula for sine and for cosine. Cosine of theta plus 90 degrees is equal to negative sine of theta, and sine of theta plus 90 degrees is equal to cosine theta. So you end up with this as your general form for the standard matrix when a transformation rotates theta radians. Now I just have a couple of, like 1 minute to finish this problem before my time runs out. So for this particular problem, cosine of negative 5 pi over 3 radians. You should pull out a unit circle, dust it off. You probably haven't used one in a while. Negative 5 pi over 3 radians. So when I think about that, it's almost 6 pi over 3, which would be almost 2 pi. Negative meaning the rotation is clockwise. So you're going to go almost all the way around to like this position here if you rotate negative 5 pi over 3 radians. If you're reading these values off the unit circle, it's going to be the same, we call it its coterminal. It's going to have the same reference point as pi over 3 radians. So the coordinates on the unit circle are the square root of 3 over 2 and 1/2. Sorry, I wrote that wrong. I misled myself with my drawing. It's 1/2 square root of 3 over 2. So cosine here is 1/2. Sine is the square root of 3 over 2. Negative sine will be negative square root of 3 over 2. Cosine is 1/2. This is your answer. This 2 by 2 matrix here would be your answer for this example B.